Hello YouTube. In this video we will be going over the following topics. So first we'll start off by introducing the concept of linear combinations of vectors. After that we'll be able to introduce the span of vectors. After that we will be able to introduce finite dimensional vector spaces. Then we will talk about the linear independence of vectors. After that, we can establish what a basis of a vector space is, and finally, we will finish off by talking about the dimension of a vector space. So, without further ado, let us begin. Starting off with linear combinations, we give the following definition. We say that this sum here, where a1 to an are scalars, so they are elements of our field F, and v1 to vn are vectors from our vector space V over F. So this is a linear combination of the vectors v1 to vn. So any sum of this form, where the a's are scalars and the v's are vectors, is a linear combination of those vectors. So let's provide an example. So here we have that. Let's take the real plane, so the set of all ordered pairs. Take any arbitrary ordered pair, any point in the plane, then this can be written as this. So we have that. Any point in the real plane can be expressed as a linear combination of the vectors 0, 1 and 0, 1 and 1, 0. So here we have, as you can see, this is the form. X and Y are scalars, here are vectors, so any point in the plane can be expressed as a linear combination of these two vectors. So here's a little picture. So here's the green arrows are like the vectors. So here we have 1, 0, and here we have 0, 1. And now to get this V, which is the vector that points to the point xy, well, we have to scale our vector 1, 0 by x, so to go x units in that direction, and then we have to go y units in this direction of our 0, 1 vector. So to get to here, we go here, and then we go here, which is just the sum. So that would be a linear combination. Now we can move on to span. Now we move on to the concept of the span of some given vectors. So we give the following definition. We say that the span of vectors v1 to vn is the set of all linear combinations of the given vectors. Written using set notation, so we say that span of these vectors, which we will write this way, so this is that set, this is the span, well, that is just equal to the set of all linear combinations of the given vector. So the a's are scalars and the v's are vectors. So let's provide an example. Previously we've shown that any vector in the real plane, so any ordered pair of real numbers, can be written as this linear combination of these two vectors. So we have that. Whatever vector I choose from R squared, it belongs to the span. So we've seen that every point can be written as a linear combination. So this point belongs to the set, well, of all linear combinations of these two vectors. So just by using the vectors 1, 0 and 0, 1, we can get all the other vectors v in R squared. And now we prove the following result about the span of some vectors. So theorem, the span of vectors v1 to vn is the smallest subspace such that each vector vi is contained within it. So we have to show three things about span. We have to show that it is the smallest subspace, so it is a subspace, and it's also the smallest subspace such that it contains each given vector v. So let's show all of this. So first, let's show that it's the smallest subspace. So let S be a subspace such that, well, it contains all of the vectors vi. Now, since S is a subspace, by definition, it is closed under addition. So if I've got some vectors x, y, I know that x plus y is in S. And it is closed under scalar multiplication. So if x belongs to S, well then alpha times x also belongs to S, where alpha is an arbitrary scalar. And now combining these two facts, well, since S is a subspace, it is closed under these two additions, and it contains under these two operations, and it contains each of the VI's, well, that means that whatever linear combination I create using the vectors, it also belongs to S. So every element of the span of these vectors is in S, which means that span is a subset of any given such subspace. So it is the lower limit. It is the smallest set such that this holds, that it contains all of the vectors vi. So that would be showing that it is the smallest. Now let's show that span is a subspace. So take arbitrary two vectors x, y from our span and some arbitrary alpha scalar. And now we ask ourselves, is it the case that this sum, this linear combination, belongs to span? Well, since x and y belong to span, that means there exist scalars such that, well, x can be written as this linear combination and y can be written as this linear combination. Hence, we have that x plus alpha times y. When I multiply with alpha all of the elements over here, and when I add up the corresponding elements, so I group all the terms with v1, v2, and so on, I will just get that x plus alpha times y is just some c1 times v1 plus all the way to cn times vn. So it's just another linear combination of vectors. Well, that means that by the definition of span, it is also an element of span. So we have shown that. From this, it follows that this also belongs in span. That means that span is a subspace. And finally, we have to show that span contains each of the VI's. Well, every VI can be written in the following way. So just as a linear combination where I put zeros everywhere besides, well, the vector vi. I just put 1 next to it. And now we've expressed every vi as a linear combination. Well, that means that every vi belongs to span. So that's the end of the proof. We've shown that it's the smallest subspace that contains each of the vi's. So that would be everything about span that we're interested in. And now we can move on to introducing the concept of finite dimensional vector spaces. Now that we've covered the span of some given vectors, we can introduce the concept of finite dimensional vector spaces. So the following definition, we say that V of F's or vector space is finite dimensional if there exist some vectors v1 to vn belonging to V such that the span of those vectors is equal to V. So let's give an example. As previously shown, we had that any vector in R squared belong to the span of these two vectors. Well, that means that the span of those two vectors is equal to R squared. So we have that R squared is a finite dimensional vector space. Now, to show an example of a non-finite dimensional vector space, we have to introduce the following concept regarding polynomials. So we say that a polynomial, some p, that belongs to the vector space of all polynomials, is of degree m, where m is a natural number, so of degree 0, 1, 2, and so on, is a polynomial of the following form, so all the way to am times z to the mth, where, of course, am has to be different from 0, for if it were equal to 0, well, then we wouldn't have the mth degree term. So, yeah. this is the definition of what it means for a polynomial to be of degree m. So now let us show that the vector space of all polynomials is not finite dimensional. Well, to show that, let's proceed in the following manner. So let us define the following set S as follows. So S will be the set of all subsets of polynomials. So S will be a set that contains other collections of polynomials such that the span of that collection of those polynomials has to be equal to the vector space of all polynomials of degree m. So this is the set of all polynomials. This is the set specifically of all polynomials of degree m. So in S, the only elements in S are these collections of polynomials such that the span of that collection of polynomials is equal to the set of all polynomials of degree m, and we ask of the elements to be finite collections. And now, since, for example, S of m, this given set over here is finite, and this is just a collection of polynomials. So one is a polynomial z, just the unknown variable z is a polynomial z to the mth, all the way to the z to the mth. All of these are polynomials. So this is a subset of the set of the vector space of all polynomials. And you can verify yourself that the span of this set, if you were to make linear combinations using these elements, these vectors, you would get the set of all polynomials of degree m. So we have that this set over here is definitely not empty, since I've just presented an element that definitely belongs to it. So this set S, it makes sense to define this set for something like this does actually exist, for we have just provided an example of an element that belongs to S. Now that we've established our S, we proceed in the following manner. So whatever S' I take from S, we have that by the definition of S. The span of S' is equal to the vector space of all polynomials of degree m, and we have that the vector space of polynomials of degree m is always a proper subset of the set of all polynomials. So if I have all the polynomials of some given degree m, no matter how big I choose my m, my natural number to be, there will always exist polynomials of higher degrees that do not belong to this set. So this is always a proper subset, no matter what m I pick. I can choose 1 billion, it's still not the whole set of all polynomials. So whatever S' we take from S, we have that the span of S' is equal to some set of to the whole set of the polynomials of degree m, and that is a proper subset of the whole space of all the polynomials. So no matter what S' I choose from S, it can never span the whole space of polynomials. So there does not exist a finite collection of polynomials that spans the vector space of all polynomials. So, by definition, it is not finite dimensional. For it to be finite dimensional, there has to exist a finite collection of vectors that span it, but we've just demonstrated that no matter what finite collection I try to choose, it can never span the whole space P of f. And that concludes the proof. So, since we've seen an example of a non-finite dimensional vector space, we introduce the following definition. We say that a vector space V of f is infinite dimensional if it is not finite dimensional. So, the vector space of all polynomials is infinite dimensional. So, that would be it for finite dimensional vector spaces. Now, we will move on to the concept of linear independence. Moving on to linear independence, we say that the vectors v1 to vn from our vector space V of f are linearly independent if the following holds. So if I try to express the 0 vector as a linear combination of the given vectors, then the only way to achieve that is by setting all the scalars equal to 0. So that's what it means for vectors to be linearly independent. If they are not linearly independent, we say that they are linearly dependent. So let's look at an example. So here we have this linear combination of vectors, the vectors 1, 0, 0, 1, which is equal to this, and we set that equal to the 0 vector. And, well, from our vectors being ordered pairs of real numbers, it follows that x and y have to be equal to 0. So these vectors are linearly independent. Whilst in this example, where we have the vectors 1, 0, 0, 1, and 1, 1, we can make a linear combination where not all the scalars are 0, but we still get the 0 vector. That means that these three vectors are linearly dependent. And now notice that if I put these vectors in an ordered list, so this is my first vector, my second, and my third, we have that, for example, 0, 1 can be expressed as list linear combination, and more interestingly, we have that our third element, our last element, can be expressed as a linear combination of the first and the second vector. So this will inspire us to formulate a result to see that result a bit better. So here we have that the ordered list of these vectors is linearly dependent, and our first vector is different from 0. Then we have that there exists some index j from the numbers 2, 3, since our list is of length 3, such that the vjth vector, in our case the third vector, belongs to the span of all the vectors that come before it. So v3 can be expressed as a linear combination of v1 and v2. That means that it belongs to the span of these vectors. And we also have that the span of our original list is equal to the span without vj for if since our third vector, our vj in this case, belongs to the span of these two vectors. If I were to remove it from the list, I wouldn't have removed anything significant from the span, since this element was already contained within the span of these two vectors. So the span of our original three vectors is the same as the span of these two vectors after I have removed v3. So now we state formally this observation. If we have some ordered list of vectors that is linearly dependent and the first vector is different from 0, then there exists some index j from the set 2, 3 all the way to n, such that the vj vector belongs to the span of all the vectors that come before it, and the span of the original list is equal to the span without that vj in the list. So let's prove this. So let this list be an ordered list of linearly dependent vectors in our vector space V of f. Now, by the definition of linear dependence, there exist scalars a1 all the way to an, not all 0 due to the linear dependence, such that this linear combination is equal to 0. And now, if all scalars a2 all the way to an were 0, then we plug in a2 all the way to an over here, they're all 0, then we're left with a1 times v1 is equal to 0. Now, since v1 is different from 0, that would mean that a1 would have to be equal to 0, but then all the scalars would be equal to 0, which is impossible, since by the definition of linear dependence, at least one of these scalars is different from 0. Hence, not all of a2 all the way to an are equal to 0. So we assume that these were equal to 0, and we got a contradiction. So that means that this cannot be the case. So now that we've established that they're not all 0, we can define j from the set of indices all the way to n to be the largest element, such that the ajth scalar is different from 0. So the ajth is the scalar which is different from 0, and all the other scalars that come after it are equal to 0. So since it is the largest element such that the scalar is different from 0. So aj plus 1, aj plus 2, all the way to an are 0. So we have that from our original linear combination. We just get this. We get from a1 to aj, and all the other scalars are 0, so we don't have to write that. And now we can just express the vector vj from here. Since aj is different from 0, we can divide by it. So we just transfer all of the vectors before vj from the left side to the right side of the equation, and then divide by aj to get this. And now this is a linear combination of the vectors v1 all the way to vj minus 1. Here should be a minus 1. So we have that vj belongs to the span of all the vectors that come before it. Now let us show that the span of the original list is equal to the span of the list without vj. So take some arbitrary u from the span of the original vectors. By the definition of belonging to the span, that means that this vector can be expressed as a linear combination. And now we have this expression for vj, and we can use that to substitute for vj in this linear combination. And after we have done that, well, we've gotten rid of vj, and all the vectors that remain are the same besides vj. So we see that u can be expressed as a linear combination of all the vectors without vj. That means that u belongs to the span without vj. So the two spans are the same, since I've taken an arbitrary element from the span, and we've shown that it belongs to this span as well. So these two sets are equal. And now we have the following result. If this list is such that it spans our vector space, so this is a spanning list of vectors, and if this ordered list of vectors is linearly independent, then the number of elements in the linearly independent list has to be less than or equal to than n. So any list of linearly independent vectors has to be of length less than or equal to than any spanning list of vectors of the vector space V. So let's show that this inequality holds. So let this ordered list of vectors be a spanning list, so it spans the vector space and there's n elements in it. And let this be a linearly independent list in V, and there are m elements here. And now in the step 1, so we will demonstrate a procedure, and we will show that that procedure terminates, and from that we will get our result. So in the first step of this procedure, we have that the span of these vectors is equal to V. So if I add any other vector from V to my original spanning list of vectors, then we get a linearly dependent list of vectors. To see that that is the case, if V belongs to V, well, then it belongs to this span, so it can be written as a linear combination of vectors, and then I can write this linear combination. So minus 1 times V plus, well, just V, its linear combination, and this is equal to 0. And this is a linear combination of the vectors in this ordered list, so this list is linearly dependent. So we will, to our original list, our spanning list of vectors, we will add W1 to this list. And now, since this list is linearly dependent, and W1 is different from 0, due to the linear independence of this list is a linearly independent list of vectors, and none of these vectors can be 0, for if any of the vectors were 0, then this list won't be linearly independent. So we know that W1 is different from 0. So by the linear dependence lemma, we get that there exists some index j from 1 to m, such that Vj belongs to the span of all the vectors that come before it, and the span stays the same, so after I remove that Vj. So we add W1, and then we remove this Vj that is guaranteed to us by the linear dependence lemma. And now in step j, so in step 2, in step 3, and so on, so after step j minus 1, after the previous step, we get a new list B of vectors, for example, W1, W2, all the way to Wj minus 1, and the remaining V's over here, such that the span of this list is V. So now again, we add Wj to our list B, and now B has to be linearly dependent. So by the linearly dependence lemma, we can remove some vector from the list to get rid of the linear dependence. The vector that causes the linear dependence can't be one of the W's due to this list of vectors, so the list of W's being linearly independent. So none of these, since all of these W's are linearly independent, none of them can be causing the list to become a linearly independent list of vectors. So one of the V's has to be a problem. So we remove some Vi from B. And again, after we've removed the Vi, the span of B is equal to V. So this is the procedure. And now, if we got rid of all the V's, and there was at least one W left to add, so some Wm, for example, then we get that W1 all the way to Wm is linearly dependent, which is impossible since this is a linearly independent list of vectors. So there cannot be more W's than V's, since that would cause a contradiction due to the linear independence of our W's. Hence, there must be at least as many V's as there are W's. So we will be adding W's and removing V's for their list. And after we've added all the W's, well, either there was the exact number of V's as there were W's, or there are still some V's left in the list. Either way, we have that M, the number of vectors in our linearly independent list, has to be less than or equal to than n. So that's the end of that proof. And now we can show the following result. So if U is a subspace of our vector space V of f, and V of f is finite dimensional, then U is also finite dimensional. So let's show this. Well, if U is equal to just the zero subspace, then U is finite dimensional. For just take the span of the zero vector and you will get this subspace. So it's finite dimensional. So if it is not equal to the zero subspace, well, that means there must exist at least one U, we will take some U1, such that it is different from the zero vector. So take that U1 from U, which is different from zero, and now take its span. And now if the span of that vector is equal to U, well, U is finite dimensional and we're done. If span of U1 is not equal to U, well, then take U2 from U without the span of the first vector. So we have our space U, and from it we remove all the vectors that I can get using the vector U1. And now I take some U2. And now I look at the span of those two vectors, and if that is equal to U, again, we're done. Finite dimensional. If not, repeat this process. So just take from U, remove all the elements that belong to the span of our previous vectors, and take some new element, and so on. And now we have to show that this process stops at one point, so that this cannot go to infinity. So since this is an ordered list of linearly independent vectors in U, due to the way we're choosing our u1, u2, we're always picking a vector that does not belong to the span of the previous vector. So it has to be linearly independent from all the previous vectors. So when we pick up new u's and form our new lists, we always have an ordered list of linearly independent vectors in U. And now previously we've shown that every ordered list of linearly independent vectors has length less than or equal to then some spanning list of the vector space. And now since this is an ordered list of linearly independent vectors in U, and U is a subspace, then it is also a list of linearly independent vectors in V. Now the length of every linearly independent list of vectors in V is less than the length of a spanning list of V. And our vector space V is finite dimensional, so we know that there exists some V1 all the way to Vn such that they span the vector space V. Hence, we have that the length of this list, M, is less than or equal to than N, so there is an upper limit. So after at most n steps, this process will end. We will get vectors u1 all the way to un such that they span the vector space U. Hence, U is finite dimensional. That would be all for linear independence. And now that we have the concepts of span and linear independence, we can move on to introducing the concept of a basis of a vector space. Now we can introduce the concept of a basis of a vector space. So we say that B, which is equal to this ordered list of vectors, is a basis of the vector space V of F if the span of B is equal to V, so these vectors span the vector space, and B is linearly independent. If these two hold, then we say that B is a basis of the vector space. And now to show the significance of a basis, so the following theorem: if we have B a basis of a vector space, then every vector in V has a unique representation as a linear combination of the vectors from B, and vice versa. If every vector in V has a unique representation as a linear combination of some vectors, then those vectors are a basis of the vector space. So if we have a basis, then every vector in the vector space can be represented in a unique manner as a linear combination. So let's show this. So going from the left to the right, showing this implication. So let B be our basis of our vector space V of F. Take some arbitrary vector V, and let's say that it has two representations. So V can be written as this linear combination and this linear combination. Then once we subtract these two equalities, we get the following expression. So we get this linear combination to be equal to 0. And now, since the vectors v1, v2, all the way to vn are linearly independent, since B is a basis, we have that all these scalars have to be equal to 0, which means that every one of these is equal to 0, which means that ai is equal to b of I for all I that go from 1 to n. So these two representations are actually the same. So that means that there is only one representation for the vector v. Now in the opposite direction, so let's suppose that every vector in the vector space has a unique representation as a linear combination of these given vectors, v1 to vn. Well, then we have that our 0 vector can be expressed this way. And since every vector has a unique representation, well, this means that this has to be the only representation. So if I set some arbitrary linear combination to be equals to 0, knowing this, I conclude that the scalars have to be 0. And since So we've shown that the vectors are linearly independent since we've shown that this holds. And since every vector v can be expressed as a linear combination of these vectors, well, that means that these vectors span the vector space. So we have linear independence, and we have that they span the vector space. Hence, B is a basis of V. So that concludes that proof. Moving on to the next result, we have that any spanning list of the vector space V can be reduced to a basis of V. So let B be some spanning list of V. And now, if B is linearly independent, well, we're done. If it is not, then by definition it is linearly dependent. So by the linear dependence lemma, we can remove some Vj without changing the span of B. Remove the Vj. Now ask ourselves again, if B is linearly independent, well, then we're done. If not, again, it's linearly dependent, and we can repeat the process above. We can remove another Vj. And now this process will end after a while, since the span of the empty list is equal to the 0 subspace, and the empty list, which has no elements, so 0 elements, is linearly independent by definition. We get that 0 is less than or equal to than n, so the length of our starting spanning list. So after at most n steps, the process will end. And it only ends when we end up with a B that is linearly independent. So after at most n steps, we will have ended up with B that spans V and is linearly independent. So a basis of our vector space V. Now, using that result, we can just show the following. Every finite dimensional vector space V of f has a basis. So by definition, there exists some vectors v1 to vn such that the span of those vectors is equal to v. And now, using the above result, we can reduce that spanning list to a basis of v, hence showing that every finite dimensional vector space has a basis. Now, the following result, any linearly independent list, B, in our vector space, can be extended to a basis of V. So let B some linearly independent list of vectors in V. If the span of B is equal to V, well, then we're done. We have a basis of B. If not, that means that B does not span V completely. Well, then there exists some V in V without the span of B, and V is different from 0. So we just add that V to our B. And now repeat this process. So just add a vector, see if it spans. If it does not span, add another vector from V without the bigger span now. And now, since we're always adding V's that belong from this set, B is always linearly independent. Thus, with V being finite dimensional, there exists some spanning list of vectors W1 to Wm, so that spans V. So, and this list, we have that its length is always less than or equal to than the length of this spanning list. So, after a while, this process will terminate, and we will have gotten a B that is linearly independent and also spans V. So we will get a basis, thus showing that any linearly independent list of vectors can be extended to a basis of V. And now we can show the following. If U is a subspace of our vector space V, then there exists another subspace W such that V can be written as the direct sum of those two subspaces. So let's show that. So since U is a subspace of V and V is finite dimensional, then U is also finite dimensional. Hence, it has a basis. So let B of U be the basis of our subspace U. And now that basis can be extended to a basis of the whole vector space V. So B let's write the whole basis like this. So all the vectors from U and then some extra vectors W's such that B is a basis of V. And now we just let W, our new subspace, be the span of those vectors we added to extend the original list. And now we have that, well, V can be written as the sum of U plus W, since every vector in V can be written as a, well, linear combination of these vectors. And now to show that this is a direct sum, we have to show that the only way to get the zero vectors using vectors U and W from these subspaces is by using, well, the zero vector from U and the zero vector from W. So if I take some little u and little w, some arbitrary vectors from those subspaces, well, they can be written as these linear combinations. So u is equal to this linear combination and our little w is equal to this linear combination. And now we set it equal to 0. And since B is a basis of our vector space V, the vectors are linearly independent. Hence, all the scalars have to be equal to 0, and that means that our little u has to be equal to the 0 vector, and our little w has to be equal to the 0 vector. So we have that V is equal to the direct sum of u and w. And that would be it for basis. And now we're just left to introduce the concept of the dimension of a vector space. And at the end, we can go over the dimension of a finite dimensional vector space. Before we can give the definition, we have to show the following result. If V is a finite dimensional vector space, then the lengths of all of its bases are the same. So, let B1, B2 be basis of V, which is finite dimensional. Well, we have that every linearly independent list of vectors is of length less than or equal to every spanning list of V. So we have that M is less than or equal to than N, where M is the length of a linearly independent list, and N is the length of a spanning list. And now, B1 is a basis, so it is linearly independent. B2 is a basis, so it spans V. So we have that the length of B1 is less than or equal to than the length of B2. And now we just use the same reasoning, but exchange the basis. So we have that B2 is less than or equal to than B1. So we have that their lengths have to be the same. And now that we've established that all the bases have the same length, now we can introduce the concept of dimension. Now this definition can be valid and have sense, meaning for we say that the dimension of V, or finite dimensional vector space, is the length of any of its bases. So the dimension of V is equal to the length of B, where B is some basis, some of its bases, one of its bases. So for example, we have that B, like this, is a basis of R squared. So we have that the dimension of R squared is equal to 2. In general, this basis over here is called the standard basis of f to the n. So the ordered n-tuples of elements in some field. So the dimension of f to the n is equal to n, since there are n vectors here. For example, if I look at the vector space of all polynomials of degree m, well, the dimension is m plus 1, since here is a basis of that space. So we have z to zm, there's m of these, and we have 1, so z to the 0th. So we have m plus 1 elements here. So the dimension of this vector space is equal to m plus 1. And now we can show the following, that if U is a subspace of our finite dimensional vector space V, then the dimension of U is less than or equal to V. So since U is a subspace of a finite dimensional vector space V, U is also finite dimensional. thus there exists a basis of u, some b of u, these vectors over here. Now, we can extend this to a basis of v, some b of v, with all those vectors and some extra vectors. Now, either we added vectors to bu, or bu was already a basis of v. Hence, the length of bu is less than or equal to than bv. So the dimension of u is less than or equal to the dimension of v again. So this is a basis of u, and now to get to a basis of v, well, either it's already a basis of v, or I have to add some vectors until I get a basis of v. So this length is less than or equal to than this. If v is finite dimensional, then every spanning list of vectors in v with length of dimension v is a basis of v. So if I have a spanning list with n elements and the dimension of v is n, then the spanning list is a basis. So let the dimension of v be equal to n, and let this list of vectors span v. Well, the list, so any spanning list can be reduced to a basis of v, so this list can be reduced to a basis of v, but every basis of v has length n, and this already has n elements in it, so the reduction is a trivial one. No elements are removed from the list. Thus, our list was already a basis of v. If v is finite dimensional, then every linearly independent list of vectors in n with length dimension v is a basis of v. So again, let the dimension of v be equal to n, and let this be a list of linearly independent vectors in v. So there's n of them. Now this list can be extended to a basis of v, but every basis of v is the length n. So the extension is a trivial one. Again, no elements are added. So thus this list is a basis of v. Now we have the following result. If u1 and u2 are subspaces of a finite dimensional vector space v, then we have that the following holds. So if we want to calculate the dimension of u1 plus u2, then we can do so as follows. So the dimension of u1 plus the dimension of u2 minus the dimension of their intersection. So let's show that this holds. So let this ordered list be a basis of the intersection of our two subspaces, which we know is non-empty since at least they share the zero vector. So the dimension of the intersection is equal to m, since there are m vectors in this basis. And now, since this is a basis of the intersection, it is linearly independent in the subspace u1. So it can be extended to a basis, this over here, this list, of u1. So now we have the dimension of u1 is equal to m plus j, these vectors over here. Now we can also extend the same original list, the basis of the intersection, to a basis of the subspace u2. So the dimension of u2 will be equal to m plus some k. And now, to show that the above equation holds, we will show that this list, so all of the vectors, is a basis of u1 plus u2. This will complete the proof because the dimension of this, if this is the basis of this, then the dimension of this is equal to m plus j plus k, which can be rewritten to the following. So we add and subtract an m, and then we group terms like this, and then we have that this is equal to, well, this is the dimension of u1, this is the dimension of u2, and this is just the dimension of the intersection. So by showing that this list is a basis of the sum, we will have completed the proof. So let's look at the span of all of these vectors. The span of all of these vectors contains u1 and u2. So since u1, the basis of u1 are all of these vectors, so u1 is contained, since we have all of the vectors we need to get u1, and the same goes for u2, since we have these vectors and these, so they're contained. And since we have u1 contained and u2 contained, so we also have that the span of all of these vectors contains u1 plus u2. So now we need to show that the list is a basis of u1 plus u2. We only need to show that it is linearly independent, since we already have established that the span of these vectors contains this. So suppose that this linear combination of all of the vectors in the list is equal to 0. And now rewrite this to get the following. So I've left these over here and transferred everything to the right side of the equality. So now from this, since this belongs to the intersection of our subspaces, it definitely belongs to the subspace U1. And this also belongs to U1. So we have that this belongs to U1. And now since all the W's, all of these vectors, belong to U2, we have that this belongs to the intersection, since it belongs to U1 and it belongs to U2. And now, since this is a basis of the intersection, we can write this as some linear combination of the vectors in the basis. So we have this. And now, since this list is some basis of one of the subspaces, it is linearly independent. So we have that this equals to 0 implies that all of these scalars are 0. So this turns this expression, so we've just shown that all the C scalars are 0, so this turns into this. And now, since this is a basis, the vectors are linearly independent, so we get that all of the scalars have to be 0. And then finally, we've shown that all the A's, all the B's, and all the C's are equal to 0. Thus, this list is a basis of U1 plus U2. Thus completing the proof, since we've shown that this is a basis, and then we have that this holds. And our final theorem for today: if V is a finite dimensional vector space and U1 to UM are subspaces of V such that their sum is equal to V, and the dimension of V is equal to the sum of the dimensions of the subspaces, then it follows that V is actually a direct sum of all of these subspaces. So, choose a basis Bj for each Uj, which we can do since each Uj is finite dimensional, so it has a basis. Form B by putting together the Bj's in one list. So each Bj is a list of some vectors, a basis, and we just form B by taking all those vectors and putting them in order to form a new list B. And now we have that span of B is equal to V, and we have that the dimension, the number of elements in B is equal to the dimension of V. So B is a basis of V. So we have that B spans V, and we have that the length of the list is equal to the dimension V. So it has to be a basis due to one of our previous results. And now we have to show that it is a direct sum. So let U1 belong from, let's let U1, little u1 be from big U1 all the way to little um from our subspace um, and let that, so we sum them up and set them equal to 0. And now we would like to show that all of these are equal to the 0 vector. So we can write each uj as a linear combination of the basis vectors from bj. So if I, for example, u1 since it belongs to the subspace u1, and u1 has a basis b1, u1 can be written as a linear combination of those vectors. So substitute each of these u's with the appropriate linear combination. And now we have written 0, after we've performed all of those substitutions, we have written 0 as a linear combination of the basis vectors from B. Thus, all the scalars in the given linear combination of uj must be 0. So the final linear combination, it is a linear combination of vectors that are linearly independent. So all the scalars are equal to 0. So all the scalars that go up into the linear combination of a certain uj are equal to 0. That means that each uj must be equal to the 0 vector. Thus, each uj is equal to 0, which proves that B is equal to the direct sum of the subspaces. And that concludes this video. So if you find my content useful, consider, liking the video, commenting your feedback, maybe even subscribing. It helps out a lot. And yeah, that's about it. Next video, we will be going over exercises, reviewing all of this material, of all of the concepts in this video. So thanks for watching. Have a good one.